Hi, I welcome you all to this session on lasers where we are going to study anything and everything about lasers. And taking you along on this journey is Dr. Yunus Jerusha, an assistant professor of physics. Lasers are key components of many of the products that we use every day. Consumer products like Blu-ray and DVD players rely on laser technology to read information from the disc. Barcode scanners rely on lasers for information processing. Lasers are also used in many surgical procedures such as LASIK eye surgery. In manufacturing, lasers are used for cutting, engraving, drilling, and marking a broad range of materials. So, what exactly is a laser? It is an abbreviation for light amplification by stimulated emission of radiation. To be very precise in its definition, a laser is a device that produces a coherent beam of optical radiation by stimulating electronic, ionic, or molecular transitions to higher energy levels. When they return to the lower energy levels by stimulated emission, they emit energy. So that is what is a laser. The first and most important characteristic of a laser beam is its directionality. It possesses high directionality. Laser light travels in a single direction with a narrow cone of divergence defined in terms of the divergence angle. Divergence angle is twice the angle made by the outer edge with the axis of the beam, and the angular spread of the beam on one side of the axis is given by theta is equal to d prime by L, and this in turn is given as beta lambda by d. The second most important characteristic of a laser beam is its intensity. The intensity of light is defined as the energy passing per unit area per second through a point normal to the direction of flow. The peak intensity at the spot center is given by I naught, which is 2p by pi omega square, where P is the laser power output and W is the beam radius. A laser beam is highly intense because it emits light as a narrow beam due to its directional nature, and therefore the intensity remains high even at a large distance from the laser source. A laser beam possesses extraordinary monochromaticity. If delta nu is the frequency of a spectral line of frequency nu naught, then the degree of monochromaticity is defined as epsilon is equal to delta nu by nu naught. Smaller is the value of epsilon, higher is the monochromaticity of the light. And for a laser source, epsilon is 10 power minus 12, whereas for an ordinary light source, epsilon is high at 10 power minus 5. A laser light source is also said to possess high coherence. The degree of coherence is the measure of phase correlation in the radiation field at different locations and different times. When we say coherence, a laser beam must possess temporal as well as spatial coherence. Temporal coherence is the ability of a light beam to form fringes with a delayed version of itself, while spatial coherence is the ability of spatially separated points in a wavefront to form fringes. Spot the differences between the two pictures shown here. The first picture is that of ordinary light and the second picture is that of laser light. In the first picture, we see many colored lines. whereas in the second picture we see only one colored line. Also, at the output side, the waves are of different colors, moving in different directions, and they are not in phase. Whereas in the second picture, we have the same color, the waves are moving in one particular direction, and all these waves are in phase with each other. Let us put all these differences which we've just seen in scientific terms in the coming slide. Ordinary light is incoherent, whereas laser light is highly coherent. Ordinary light, as we saw, is non-directional, whereas laser light is highly directional. Ordinary light is less intense. Laser light, on the other hand, is highly intense. There is more angular spread to ordinary light, whereas laser light has less angular spread, and therefore ordinary light cannot be focused to a sharp spot, whereas laser light can be focused to a sharp spot. And some of the examples of ordinary light are sunlight, mercury vapor lamp, etc. And for laser light, we have the helium neon laser, carbon dioxide laser, diode laser, and many more. The basic concepts which are involved in the formation of a laser beam are absorption, spontaneous emission, stimulated emission, and population inversion. When light falls on a material, there is an interaction of the photons in the light with the atoms in the material, giving rise to three different phenomena called as absorption, spontaneous emission, and stimulated emission. Absorption is the process where an electron in an atom can be excited from an energy level E1 to a higher energy level E2 by absorption of a photon of energy h nu equal to E2 minus E1. Spontaneous emission, on the other hand, has the atom decaying from a higher energy level E2 to a lower energy level E1 through the emission of a photon with energy h nu. It is a completely random process emitting photons which move in all possible directions. Finally, we have stimulated emission, where atoms in the upper energy level can be triggered or stimulated in phase by an incoming photon of a specific energy, mostly h nu equal to E2 minus E1. The resultant of this stimulated emission is a set of coherent photons all moving in the same direction and thereby possessing a high intensity. Let us now explore Einstein's theory of radiation in a comprehensive manner. We know that when light is absorbed by atoms or molecules, they go from the lower energy level E1 to the higher energy level E2, and during the transition from the higher energy level E2 to the lower energy level E1, light is emitted from the atoms or molecules. Let us consider an atom exposed to a photon of energy E2 minus E1 equal to h nu. Then, three distinct processes takes place called as absorption, spontaneous emission, and stimulated emission. Towards the end of this theory, we'll be finding out what are called as the Einstein's A and B coefficients, and also we will be able to tell whether stimulated emission takes place naturally or spontaneous emission takes place naturally. The first process to take place when light falls on a material is stimulated absorption, or in very simple terms, absorption. The rate of absorption or the number of absorption transitions per unit time is denoted by R12. R12 is proportional to N1, the number of atoms in energy level E1 per unit volume of the medium, and R12 is also proportional to rho of nu, which is the energy density of incident radiation. In order to remove the proportionality sign, we introduce a proportionality constant denoted by B12, where B12 stands for the probability of absorption transitions per unit time. Therefore, the rate of absorption is given by R12 is equal to N1 B12 rho of nu. In general, atoms in the higher energy state E2 will not stay there for long. Rather, they come to the ground state or the lower energy state by emitting a photon of energy h nu. Such types of emission take place by two methods, the spontaneous emission method or the stimulated emission method. Let us first have a look at the spontaneous emission method. Here, the rate of spontaneous emission or the number of spontaneous emission transitions from state E2 to state E1 per unit time is denoted by R21 SP. This R21 SP is proportional to N2, which is the number of atoms in the energy level E2 per unit volume of the medium. Now, in order to remove the proportionality sign, we introduce a constant denoted by A21, and A21 stands for the probability of spontaneous emission transitions per unit time. Therefore, R21 SP is equal to A21 N2. The next method by which an atom can come down from a higher energy state E2 to a lower energy state E1 is stimulated emission. The rate of stimulated emission or the number of stimulated emission transitions from state E2 to state E1 per unit time is denoted by R21 ST. R21 ST is proportional to N2, the number of atoms in the energy level E2 per unit volume of the medium, and also R21 ST is proportional to rho of nu, where rho of nu stands for the energy density of incident radiation. In order to remove the proportionality sign, we introduce a constant called as B21, which denotes the probability of stimulated emission transitions per unit time. Therefore, R21 ST is N2 B21 rho of nu. Einstein's theory of absorption and emission of light by an atom is based on the Planck's theory of radiation. Also, under thermal equilibrium, the population of the energy levels obeys the Boltzmann's distribution law. There is another one which occurs at thermal equilibrium, where the rate of upward transitions must be equal to the rate of downward transitions. That is, the rate of absorption must be equal to the rate of emission. Therefore, we have here the rate of absorption to be equal to the sum of the rates of spontaneous emission and stimulated emission. We now substitute for the rate of absorption as N1 B12 rho of nu and the rate of spontaneous emission as N2 A21 and for the rate of stimulated emission as N2 B21 rho of nu. The next step, we take N2 B21 rho of nu to the LHS and we have this expression where we have N1 B12 rho of nu minus N2 B21 rho of nu equal to N2 A21. Removing rho of nu, which is common in the terms which are there on the left hand side, we have rho of nu into N1 B12 minus N2 B21 to be equal to N2 A1. Rearranging the terms and finding out what is rho of nu, we have rho of nu therefore to be equal to N2 A21 divided by N1 B12 minus N2 B21. We name this equation as equation number 4. We now proceed to divide the numerator and denominator in the RHS of equation 4 by N2 B21. On division of the numerator by N2 B21, we obtain A21 by B21. It is written as the coefficient here. Next, the division of the denominator terms gives us N1 B12 divided by N2 B21 minus 1. The reason why we have a 1 here is N2 B21 and N2 B21 in the numerator and denominator get cancelled with each other. This equation we call as equation 5. From Boltzmann's distribution law, the number of atoms in the excited state N at temperature T is given by N is equal to N0 exp minus En divided by kBt, where N0 stands for the number of atoms which are there in the ground state and Kb stands for the Boltzmann's constant. We use this Boltzmann's distribution law in order to obtain an expression for N1 by N2, the term which is present in the denominator of rho of nu. We use the Boltzmann's distribution law and find expressions for N1 and N2, which are the number of atoms present in the first and second excited states respectively. N1 turns out to be N0 exp minus E1 divided by kBt, while N2 turns out to be N0 exp minus E2 divided kBt. We substitute these two expressions of N1 and N2 in the ratio N1 by N2. On writing these two expressions and cancellation of the N0 terms in the numerator and denominator and taking the exponential term which is there in the denominator to the numerator as well as consolidating the terms, we obtain N1 by N2 to be equal to exponential E2 minus E1 divided by kBt. We know E2 minus E1 is equal to h nu, therefore N1 by N2 is exp h nu by kBt. This is written here as equation 6. On substitution of equation 6 in equation 5, we have rho of nu to be equal to A21 divided by B21 into B12 by B21, and in the place of N1 by N2 we now have exponential h nu by kBt minus 1. This we call as equation 7. This equation 7 is quite similar to Planck's radiation law, which is 8 pi h nu cube divided by c cube into 1 by exponential h nu by kBt minus 1. We call this Planck's radiation law as equation number 8. On comparison of equations 7 and 8, we have the expressions for the Einstein's A and B coefficients to be obtained as A21 by B21 is equal to 8 pi h nu cube by c cube, and the Einstein's B coefficients B12 and B21 are related as B12 by B21 equal to 1, or both B12 and B21 are equal to each other. Some of the results and inferences obtained from the Einstein's theory of radiation are: it is a macroscopic approximation of a complex stochastic quantum mechanical process. It governs the rates of absorption or emission of photons by atoms or molecules. Absorption and spontaneous emission are the intrinsic properties of transitions in a material. The stimulated emission rate is the same as the absorption rate, that is, B12 is equal to B21. We now proceed to find the ratio of the magnitudes of stimulated to the spontaneous emission rates. We use equation 2, which is R21 SP, the rate of spontaneous emission, and equation 3, which is the rate of stimulated emission. We divide equation 3 by equation 2 and we obtain R21 ST by R21 SP to be equal to B21 by A21 rho of nu, which we call as equation 9. Rearranging equation 7, which we've obtained earlier, we get B21 by A21 rho nu to be equal to 1 divided by B12 by B21 exponential h nu by kBt minus 1. But we know B12 by B21 is equal to 1. On substitution of that, we have B21 by A21 rho nu to be equal to 1 divided by exponential h nu by kBt minus 1. This we call as equation 10. Comparing equations 9 and 10, we get R21 ST by R21 SP to be equal to 1 divided by exponential h nu by kBt minus 1. In a simpler way, the ratio can be written as R21 ST by R21 SP given by R is B21 by A21 rho of nu equal to 1 divided by exponential h nu by kBt minus 1. From this, we obtain the result that in order to increase the number of coherent photons, stimulated emission should dominate over spontaneous emission. Therefore, an artificial condition called population inversion is necessary. To achieve this, there should be more number of atoms present in the higher energy level than in the lower energy level. Also, it is observed that spontaneous emission is more predominant in the optical region, which is in the ordinary light region. And to increase the number of coherent photons, obviously stimulated emission should dominate over spontaneous emission. Some of the essentials required for laser action to take place are listed now. Population inversion, latent or active medium, optical resonator, pumping mechanism. There are different kinds. Let's see what they are. Optical pumping, electrical discharge, inelastic atom-to-atom collision, direct conversion, and chemical method. And finally, we have laser action taking place. Let us look at one of the most essential requirements for laser action to occur. It is population inversion. It occurs in a state in which a substance has been energized or excited to specific energy levels. In this animation, atoms which are there in the lower energy state are excited by means of a method called as pumping to higher energy state. And from the higher energy state, these atoms come down to the lower energy state, giving out energy. This is how laser action takes place. So, we need more atoms or molecules to be in a higher excited state. The process of producing such kind of a population inversion is called as pumping. And some of the methods by which pumping can be done is by lamps of appropriate intensity or by means of electrical discharge. An atom present in the lower energy state or in the ground state is stimulated or excited to a higher energy state by means of pumping. And in this higher excited state, it remains for a very short period of time of the order of 10 power minus 7 seconds. From this higher excited state, the atom comes down to a lower state called as the metastable state, where it resides for a longer period of time of the order of 10 power minus 3 seconds. And it is from this metastable state that the atom emits laser light as radiant energy and gets transferred back to the ground state. Therefore, an atom or molecule in an excited state remains in the metastable state for a certain time called as the lifetime before making a transition to the lower state. And therefore, lifetime is a characteristic of the energy level and varies over a wide range. Most energy states have a short lifetime of the order of 10 power minus 8 seconds. But some energy states, such as the metastable state, has a longer lifetime of 10 power minus 3 seconds or even much higher. And it is from these metastable states that laser light emission takes place when the atom gets down to the ground state. This short animation will sum up whatever we've just seen till now. The atom moves from the ground state to a short-lived state and then by means of rapid decay comes down to the metastable state, and from the metastable state there is emission of energy in the form of laser light. Since the ratio of A to 1 by B to 1 is proportional to nu cube, the spontaneous emission increases rapidly with energy difference between the two energy states E2 and E1. If A21 by B21 is much less than 1, the stimulated emission will be predominant in producing a laser beam. And finally, the units for the Einstein's A coefficient A21 is second inverse, and the units for Einstein's B coefficient B12 is Hertz, centimeter square, steradian per ergs. The various components which are present in a laser setup are the active medium or the gain medium. This is the medium in which population inversion takes place, and therefore it is called as the active medium. Secondly, we have the pump or the energy source. The pump or the energy source is used to raise more number of atoms to the excited state by many types of artificial means, and therefore it is used to achieve population inversion. Thirdly, we have the total and partial reflectors or mirrors. These mirrors are used to bounce the light back and forth, and therefore the intensity of the laser light is increased enormously. Fourthly, we have the laser beam output, and the laser beam's wavelength and the power of the laser is solely determined by the active medium along with the two mirrors which are present on either side of the active medium. This is what is called as the optical resonator. There are different types of pumping mechanisms which are used to achieve population inversion. Population inversion can be achieved by exciting the medium with a suitable form of energy. This process is what is called as pumping. There are several methods of pumping a laser and producing population inversion which is necessary for the occurrence of stimulated emission. They are optical pumping, where the atoms are excited with the help of photons emitted by an external optical source. The atoms absorb the energy from the photons and rise up to the excited state. Some common examples are the ruby laser and the Diode laser. Secondly, we have the electrical discharge. Here, the electrons are accelerated to very high velocities by strong electric field, and they collide with the gas atoms, and hence these atoms are raised to an excited state. Some of the lasers which use this kind of a pumping method are the gas lasers such as helium neon laser, carbon dioxide laser, the argon laser, etc. Thirdly, we have the inelastic atom-to-atom collision. In this method, a combination of two types of gases are used, say A and B, both having same or nearly coinciding excited states. And during electrical discharge, atom A gets excited due to collision with the electrons, and hence the excited A atoms now collide with the B atoms, so that B goes to an excited state. This kind of a pumping takes place in the helium neon laser as well as in the CO2 laser. The next type of pumping method is the direct conversion method. In this method, electrical energy is applied to the direct bandgap semiconductor such as gallium arsenide. The combination of the electrons and holes takes place, and electrical energy is converted into light energy directly. That's why this is called as direct conversion. And last of all, we have the chemical reaction type of pumping. Here, because of different types of chemical reactions, the atoms may be raised to the excited state. And these kinds of chemical reaction pumping takes place in what are called as dye lasers. There are various types of lasers. The first type of laser is a gas laser. Some common examples are the helium neon laser, the CO2 laser, etc. Next are the solid state lasers, with Diode and ruby laser to be the examples. Liquid lasers, a common example is europium benzoyl acetonate dissolved in alcohol. Dye and chemical lasers have their examples as rhodamine 6G laser, rhodamine B, etc. And last of all, we have the semiconductor laser, which employs mostly gallium arsenide and various other compound semiconducting materials. Of all these lasers, the most efficient laser, as is seen in this diagram, is the diode laser with a higher efficiency of around 45%. This is a size comparison chart of a semiconductor diode laser. It's so very small, of the order of a few millimeters. A list of compound semiconductor materials with different proportions and emitting laser light in the IR region is shown here. Let us look at the basic process for laser action in a laser diode. An electron which is present in the valence band absorbs a photon of energy and moves to the higher energy level which is there in the conduction band. A hole is left behind in the valence band. This is the process of absorption. This is followed by spontaneous emission, where the electron which had moved into the conduction band comes down to the lower energy level which is there in the valence band and releases a photon. This photon which comes out is completely spontaneous in nature. This photon in turn now stimulates other electrons which are there in the conduction band to come down to the lower energy level which is there in the valence band. Thereby, there is an emission of the incident photon along with a coherent emitted photon. And large number of such coherent emitted photons is what is called as the laser light in a diode laser. The first type of semiconductor laser to be seen is the homojunction semiconductor laser. The working principle of the laser is the electrons which are present in the conduction band combines with a hole in the valence band and the recombination produces radiant energy. The photon which is produced induces another electron in the conduction band to combine with a hole in the valence band and thereby stimulate the emission of another photon. The characteristics are: the type of laser we are seeing is the homojunction semiconductor laser. The active medium where laser action takes place is the PN junction, and the active center is the recombination of electrons and holes. The pumping method used here is direct pumping with the optical resonator as the polished junction of the diode. The power output is just 1 milliwatt. The nature of output is continuous or pulsed, and the wavelength emitted is in the range of 8400 angstrom to 8600 angstrom. The pumping method used in a semiconductor laser is direct pumping. Direct pumping involves the forward biasing of the PN junction. When we forward bias a PN junction, the barrier potential is lowered and thereby there is an easy crossing over of the majority carriers by means of diffusion across the junction. This leads to a higher recombination rate and thereby an emission of photons. Reverse biasing a PN junction, on the other hand, widens the depletion layer and increases the potential barrier. During this phenomenon, minority carriers are able to move freely with the applied field and not the majority carriers. The schematic of a homojunction semiconductor laser is shown here. The active medium is a PN junction diode made from a single crystalline material which is gallium arsenide. In this, the P region is doped with germanium and the N region is doped with tellurium. The thickness of the p-n junction layer is very narrow so that the emitted laser radiation has a large divergence. The junctions of the p and n regions are well polished and are parallel to each other. Since the refractive index of gallium arsenide is high, it acts as an optical resonator so that external mirrors are not needed. The upper and lower electrodes fixed in the P and N regions helps for the flow of current to the diode while biasing. We are going to analyze the operation of a homojunction semiconductor laser under two conditions. 1. Without any bias, and 2. Under a forward bias condition. First of all, let us look at the operation of this laser without the application of any bias. Due to the presence of a heavy doping in the P as well as in the N layers, the Fermi level is present within the valence band of the P type and is denoted by EFP. Similarly, on the N side, due to the heavy doping of the N layer, the Fermi level EFN is present within the conduction band of the N type. Also, it is observed that the Fermi levels on either side, that is on the P side and the N side, are aligned with each other. Now, on application of a forward bias, the direct conduction takes place. This occurs due to high current density and the presence of an active region near the depletion region. Therefore, due to the presence of the active region, which is shown in green, what actually happens here is the electrons which are present in the conduction band of the N type start moving towards the active region. Similarly, holes which are present in the valence band of the P type start moving towards the N region. Therefore, there is a continuous injection of minority carriers from the P side to the N side and similarly from the N side to the P side. This is called as minority carrier injection. Due to the injection of these minority carriers at the active region, there is a recombination of the electrons of the N type with the holes which are there in the P type. This initial recombination leads to the emission of spontaneously emitted photons. These spontaneously emitted photons in turn act as stimulants and stimulate further recombinations of electron and hole to occur in the active region, leading to the emission of more number of coherent photons. Hence, the emitted photons have the same phase and frequency as that of the original inducing photons and will be amplified still further to get an intense beam of laser. This is an animation showing the working of a homojunction semiconductor laser. It is very well observed that electrons which come from the N type and the holes coming from the P type recombine with each other, giving out photons, and when there is a sufficient build-up of intensity in the active region, we finally get the laser beam outside. The advantages and disadvantages of a homojunction laser are: first, the advantages. It is easy to manufacture this diode and thereby it is less in cost. The disadvantages are: it has a large threshold current density, the output is in the pulsed mode, divergence of the beam is large, it has poor coherence and stability, and therefore poor electromagnetic field confinement. Some of the applications of a homojunction diode laser are: it is compact and therefore can be used in fiber optic communication. It is used in the CD writer for reading and writing data. It is used as a therapeutic agent to relieve pain, and it is used in laser printers. The next type of semiconductor laser we are going to study is the heterojunction semiconductor laser. The principle of working is just the same as for a homojunction semiconductor laser, but the characteristics are different. So let's see what they are. The type of laser we are going to study is the heterojunction semiconductor laser. The active medium is the PN junction. Active center is the recombination of electrons and holes. Pumping method is direct pumping. The optical resonator here is the polished junction of the diode. The output power is in the order of a few milliwatts. The nature of output is continuous or pulsed, and the wavelength emitted is around 8000 angstrom. Now for the construction of the heterojunction semiconductor laser. It consists of 5 layers as shown. A layer of gallium arsenide p-type, which is a third layer and has a narrow band gap, will act as the active region. This layer is sandwiched between 2 layers having a wider band gap, that is, the p-type gallium aluminum arsenide, which acts as the second layer, and the fourth layer, which is the n-type gallium aluminum arsenide. A contact layer is made of gallium arsenide p-type, which is the first layer, to form at the top of the second layer for necessary biasing. All these 4 layers are grown over the substrate, which is the fifth layer made of n-type gallium arsenide. The junctions of the gallium arsenide p-type third layer and gallium aluminum arsenide n-type, which is the fourth layer, are well polished, and hence they act as an optical resonator. The upper and lower electrodes help in forward biasing the diode. In terms of the band gap of the active region, which is p-type gallium arsenide, is quite small. Therefore, p-type gallium arsenide is a narrow band gap semiconductor, while on either side of the active region we have gallium aluminum arsenide. Gallium aluminum arsenide is a wide band gap semiconductor. Therefore, on either side of the active region, which is p-type gallium arsenide, which is a narrow band gap semiconductor, we have gallium aluminum arsenide, which is a wide band gap semiconductor. Due to this narrow band gap semiconductor, we have the confinement of the photons taking place within the active region, and they are not allowed to move into the gallium aluminum arsenide, which is present on either side of it. Let us look at the operation of the heterojunction semiconductor laser using its energy band diagram. The diode is forward biased with the help of upper and lower electrodes. Due to forward biasing, charge carriers are produced in the wide band gap layers, which are the second layer and the fourth layer. These charge carriers are injected into the active region, which is layer 3. Layer 3 is the in-between layer here, where we have large number of electrons in the conduction band and large number of holes which are present in the valence band. The charge carriers are continuously injected from the second layer as well as from the fourth layer into this third layer until a population inversion is achieved. At this state, some of the injected charge carriers recombine and produce spontaneously emitted photons. These spontaneously emitted photons stimulate the injected charge carriers to emit more number of photons. As a result, large number of stimulated emissions arise and large number of coherent photons are produced. These photons are reflected back and forth at the junction and hence an intense coherent beam of laser emerges out from the p-n junctions of the active region, which is between layer 3 and 4. And the wavelength of the emitted radiation is in the IR range. This is an animation which shows the working of a heterojunction semiconductor laser. Here, electrons from the conduction band of the n-type gallium aluminum arsenide layer move to the active layer. Similarly, holes from the p-type gallium aluminum arsenide layer moves to the active layer. Once they reach the active layer, there is recombination emitting spontaneously emitted photons. These spontaneously emitted photons in turn act as stimulants, releasing more number of stimulated emission photons. These photons in turn, which are coherent in nature, bounce back and forth within the active layer region, and when sufficient intensity of the photons builds up, a laser beam is emitted. In the characteristics of the diode laser shown here, the x-axis has the current and the y-axis shows the optical power of light produced. It can be clearly seen from the figure that a gradual increase in power is noticed until a threshold point is reached. After the threshold value, a rapid increase in power is noticed even for a small increase in the current. The power produced by the laser diode also depends on the temperature associated with the device. Let us look at the advantages of a heterojunction laser. It has a very high power output, which is continuous. It has high directionality and coherence with a low threshold current density, and it's highly stable with a longer lifetime. The disadvantages are it has a high cost than the homojunction laser, and growing different layers of varied thickness poses a practical difficulty. There are many applications of lasers, some of which are listed here. It is used in laser range finding, information processing in DVDs and in Blu-ray discs, as barcode readers, in laser surgery, holographic imaging, laser spectroscopy, laser material processing such as cutting, engraving, drilling and marking, along with surface modification. Some of the applications which we listed are shown here in the form of pictures: holographic imaging, engraving and cutting, laser surgery and barcode reading. Lasers are used in a wide variety of applications in the medical arena. Let's look at some of them now. They are used in dentistry, for cataract removal, curvature correction of the eye, Laser scalpels are used for bloodless surgery, angioplasty for removal of artery blocks, to remove freckles, acne, birthmarks and tattoo, for the removal of kidney stones, and for cancer diagnosis and therapy. Let's wind this session with a small recap. In this session, we've studied about the various characteristics of a laser, the various components which go into the making of a laser, the different types of lasers, the various types of pumping, and in particular we studied about two types of lasers, the homojunction laser and the heterojunction laser. We also went about their various advantages and disadvantages along with their applications. We also looked at some interesting images of the medical applications of lasers. Thank you for being with me throughout this session. Hope you enjoyed it. Thank you for your patient listening.